The neighbors. Going berry picking.
Okay class, today we're going to learn about arithmetic. And we're gonna watch some 3 videos about it. So, are you class ready? Yeah! Well then, let's watch some 3 arithmetic videos right now. Here we go now class.
What I want to do in this video is familiarize ourselves with a very common class of sequences, and this is arithmetic sequences. And they're usually pretty easy to spot. They're sequences where each term is a fixed number larger than the term before it. So my goal here is to figure out which of these sequences are arithmetic sequences, and then just so we have some practice with some of the sequence notation, I want to define them in either as explicit functions of the term you're looking for, the index you're looking at, or as recursive definitions. So first, given that an arithmetic sequence is one where each successive term is a fixed amount larger than the previous one, which of these are arithmetic sequences? Well, let's look at this first one right over here. To go from -5 to -3, we had to add 2. Then to go from -3 to -1, you have to add 2. Then to go from -1 to 1, you had to add 2. So this is clearly an arithmetic sequence. We're adding the same amount every time. And there's several ways that we could define the sequence. We could say it's a sub n. And you don't always have to use k. This time we'll use n to denote our index from n equals 1 to infinity with, and there's 2 ways we can define it. We could either define it explicitly or we could define it recursively. So if we wanted to define it explicitly, we could write a sub n is equal to whatever the first term is. In this case, our first term is -5. It's equal to -5 plus, we're going to add 2 one less times than the term we're at. So for the second term, we add 2 once. For the third term, we add 2 twice. For the fourth term, we added from our base term, we added 2 3 times. So we're going to add 2. We're going to add positive 2, 1 less than the index that we're looking at, n minus 1 times. So this is an explicit definition of this arithmetic sequence. If I wanted to write it recursively, I could say a sub 1 is equal to -5, and then each successive term for a sub 2 and greater, so I can say a sub n is equal to a sub n minus 1 plus 3. Each term is equal to the previous term plus, not 3, plus 2. So this is for n greater than or equal to 2.
In this video, we're going to focus mostly on arithmetic sequences. Now, to understand what an arithmetic sequence is, it's helpful to distinguish it from a geometric sequence. So here's an example of an arithmetic sequence. The numbers 3, 7, 11, 15, 19, 23, and 27 represents an arithmetic sequence. This would be a geometric sequence: 3, 6, 12, 24, 48, 96, 192. Do you see the difference between these 2 sequences? And do you see any patterns within them? In the arithmetic sequence on the left, notice that we have a common difference. This is the first term, this is the second term, this is the third, fourth, and fifth term. To go from the first term to the second term, we need to add 4. To go from the second to the third term, we need to add 4. And that is known as the common difference.
Sequence means it's like a list of numbers. Okay, so notice the commas here. So it's basically just a list. A series is a sum. You're adding them together. But a sequence is a list. Now, arithmetic means that you're adding the same thing to get to the next term. And that thing that you're adding is what's called D, the common difference. Now, why do they call it the common difference? Difference means subtract. If you take 21 minus 17, what do you get? If you take 25 minus 21, what are you getting? 4. If you take 29 minus 25, what are you getting? 4. So what you can see is that common difference is actually what we're adding to get to the next term in the list or in the sequence. So that's why they call it D for difference. Now, the next thing I wanted to mention to you is that this is actually called n equals 1, n equals 2, n equals 3, and so on. This means this is the first term, second term, third term. Now, another notation that you want to pay attention to is like a sub 1, a sub 2, a sub 3, a sub 4. Let's write over here a sub 5. That means the value of the fifth term. N is the term number that you're on, but a sub n is the value of that term, what that term actually equals. So now what we want to talk about is how do we find out what the term is right here? Well, notice this is the 1, 2, 3, 4, 5, 6th term. Okay, so I'm just going to write n equals 6. How do we get to the 6th term? Well, you start off at 17, right? And then what you do is you add 4. Now, how many times are we adding 4? Well, we're adding 4 once, twice, 3 times, 4 times, 5 times. And a lot of students will say, you found the 6th term and you added 4 or 5 times. How come not 6 times? Well, the thing is, we're already on the first term. So to get to the 6th term, we only have to add 4 one less time. Okay, so if we wanted to generalize this a little bit more, you can say, well, this is a sub 1. That's the value of the first term. That's 17. Plus D, that's the common difference. That's what we're adding to get to the next term. And you want to add that D n minus 1 times. Okay, so in this case, you're adding 4 or 5 times. That's 20. Plus 17, that's 37, which makes sense because we were adding 4 each time. So now what we have is we have a what they call an explicit formula, meaning that it'll take you right to any particular term. So let's write this in a little bit more general way. A sub n equals a sub 1 plus D times n minus 1. So for this problem, we had, we had a sub n equals 17. That's the first term. Plus our common difference, which is 4, times n minus 1. Now, what I would do is I'd clean this up a little bit by distributing. Okay, 17 and negative 4 is how much? That's 13. And so now what we have is we have a sub n equals 13 plus 4n, and that'll allow us to find any term. If I want the 100th term, I put in 100. That's 413, and you got it. So it's real nice. It takes you right to that.
Okay class, now you are going to work on some arithmetic worksheets. So, do your stuff class, okay?
Okay, Miss Smith. Here we go now.
Wow. Hey guys. Do we had a great time learning about arithmetic?
Yes, Prince Nathan. We sure did, just like when I see my little brother Robert watching Mickey Mouse Clubhouse on Labor Day this week on Monday the 4th of September 2023.
Oh, hey, everybody. It is me, your adorable pal Mickey Mouse.
Gasp,
Say,
Robert.
I have a question. Do you want to come to my clubhouse?
Yes, of course I can, Mickey Mouse.
Well then. All right. Well then, come on. Let's go.
I almost forgot. To make the clubhouse appear, we get to say the magic words. Miska, Muska, Mickey Mouse. Say it with me. Miska, Muska, Mickey Mouse.
Daisy, Goofy, Pluto, Minnie, and Mickey are all here and present, and they're all waiting for all of you too as well. Ha ha ha. It's the Mickey Mouse Clubhouse. Come inside, let's come inside.
It's the Mickey Mouse Clubhouse. Donald on the desert.
You never shaped it. I could make. You did not make. One mistake. Now I gotta take a break.
Yes, we know, Nestor, but we're gonna have lunch at the cafeteria right now. Off we go now.
Polynesia is one of the most strikingly beautiful regions in the world, linked to world-famous tropical paradises such as Hawaii, Fiji, Tahiti, Tuvalu, Kiribati, and many more. But while these islands are beloved for their natural beauty, they're also at exceptional risk of losing considerable land or sinking entirely beneath the sea. Here's why so many Polynesian islands might not exist in 50 years. Hello and welcome to Geography by Jeb. Today we're off to the Polynesian Islands for our second community-voted video. And in exploring this region specifically, one story kept popping up again and again.
Heat waves aren't just setting records on land, they're also setting records at sea. Ocean temperatures are warming at an unprecedented rate, with 40% of global oceans currently experiencing a heat wave. It's the largest global ocean heat wave recorded since 1991. Chief Meteorologist Ginger Z joins me now from Key Coast Beach, Florida, with more on that. Ginger, NOAA says these unusually warm ocean temperatures, they don't just impact marine life, they can have a significant impact on coastal communities and economies. Can you explain why?
Oh, of course. I mean, there's no question that when I've been down and the water temperature is in the 90s, some places mid to upper 90s already at this time of year, there are major implications. That's 4 to 7 degrees above average for this point in the year. We would see this more like late August, early September. So what happens when we heat up then? It's going to be likely unprecedented. Here in the Florida Keys, you can see that drone video that we took earlier. These keys have a coral reef that is just south of them that protects them from storm surge. When you've got 95-degree water temperatures, that's super fuel for hurricanes that could develop. But also, if you kill off and bleach, which is likely happening as we speak, the coral, that is going to be a major issue when it comes to absorbing that water. It's nature's defense, and it's dying. And so we'll be today actually going on an urgent coral rescue to save some of that with the Florida Aquarium. Now, the water temperatures are, yes, well above average, but this is what else happens and why the economies, yes, are impacted because the fish life changes, everything changes. But also, when you're here on vacation and usually you have the water temps in the 80s and then the land is in the 90s. Well, that's a big enough difference that in the afternoon you get what we call a land sea breeze. You invite that breeze in. It's brilliant. It really cools you off. But this year, because the water temperature is so close to the air temperature, there's very little movement, very little mixing. That means stifling heat that does not see relief.
Wow. These two weather videos are so awesome. Are they, Will?
Yeah, Clara. They sure are. Best day ever.
Okay, class. Today we're gonna have a spelling bee contest. So, are you class ready for the spelling bee contest? Well then, let's go to the stage, so we can have a spelling bee contest right now. Here we go now, class.
Yay! Look, Derrick, I won this ribbon for being the winner of the spelling bee contest. See?
Yes, Vanessa, I see that. Well then, good job, Vanessa.
Thanks, Derrick.
You are welcome, Vanessa. Ha ha ha. Well, I gotta say that, this is the best spelling bee contest day ever in our life. Ha ha ha.
Oh yes, best TV show ever!